Oops, sorry guys. Looks like I forgot to post up the post for asking questions. So I guess no one could ask questions this time. But thankfully, the first few questions are impressive enough as it is. And I'll just compensate by +1 life, so we'll make it 6.5 lives. But still, sorry about that. Okay, so first few questions of homework are actually quite neat. There are a bunch of algebraic manipulations, but to know how to manipulate them correctly actually is not super obvious, even though they're the first few questions. Hence, harder 3 questions, of course. First up, we have this huge expansion is bigger than or equal to 6abc, and, well, there's not much sense looking at this right now. But first up, I might as well mention, there is the Cauchy's theorem, or the AMGM inequality for the 2 case is very, very useful. And if you don't know where to start, probably a nice fallback. It goes like this: x squared plus y squared bigger than or equal to 2xy. And if you want to prove for this, it's really straightforward. It's just you start with x minus y all squared, and anything squared where they're real numbers must be bigger than or equal to 0. Expand that out and you instantly get the answer. So I'm just going to use this without proof from now on, but the proof is really just a one-step thing. So I'm just going to use that. So I'm just going to call it the use AMGM for second case. Sure. Okay, for the first one, I can't see many things squared, so I'm just going to expand everything out. So I'm just going to go left-hand side is expanded. It's b squared c plus bc squared plus c squared a plus ac ca squared plus a squared b plus b squared a. Okay, now grouping time. Well, I don't want to group back to the original, so instead I'm going to find something else together. First up, notice there's b squared and b squared. There's a squared and a squared. There's also a c squared and a c squared. And those probably grouping together is probably not a bad idea. So if I group all the a squareds together, I get b plus c. And I hope you see the pattern. If I group all the b squareds together, I'll have c plus a. And if I group all the c squareds, I get a plus b. Okay. Looking at this, first up, I kind of want to use the theorem, except I don't really want to use it on non-square numbers. So it looks like perhaps this grouping was not the optimal pick. And obviously the first one is also not an optimal pick. So it seems like the idea is I want to group such that I have inside the brackets, instead of just these things, b and c, I probably want something like b squared, c squared. So I might try again. So instead of grouping like that, now we sort of understand what we're trying to go for here. And if we think a bit more, how do we get it so that we have b squared, c squared together? Oh, I see it. So looking at these two, they both contain c, a single c, right? So if I take the c out, I'll have b squared plus a squared. Actually, let's go a squared plus b squared. And this is exactly the type of thing I want, right? Two square numbers add together, I can just use Cauchy's inequality. So I'll just have to group the others together. So the one that has single b and c squared, single b a squared, I will group them together. And I'll get c squared, and I'll get a squared. And then finally, I can see here's they both contain a single a, and this has b squared and c squared in it. So now, hopefully this will work out. I'm going to cheat and not write full working, but having a look at these three, a squared plus b squared following our inequality, bigger than 2 times the inside of the square in times of the square. So 2ab, this is bigger than or equal to 2ca, this is bigger than or equal to 2bc. So this whole thing must be bigger than or equal to, we have c times 2 times a times b, it's 2abc. Same deal, 2abc And same deal, 2abc. And lovely, 6abc is my right-hand side. So we did have to go back a bit once we realized our factorization didn't work, but looks like it works out pretty nicely in the end. Not bad. B. We have okay, we have something that looks like square, square, square. They're already squares, so it looks like I can apply Cauchy's immediately. Except there's 3 of them, and that's not an even number. But I hope we all remember the trick with looking at these sort of things, right? The 3 square things added together idea, right? So instead of looking 3, we look at 2 at a time, 2 at a time, and 2 at a time. And if we look at each 2 at a time, hopefully when we add it together, divide by 2, everything works out. I hope it works. Let's have a try. So first one, let's look at the first pair. B squared c squared plus c squared a squared bigger than or equal to, use Cauchy's. This is bc squared plus ca squared. So this is bigger than 2bc ca, which is 2. It is a, b, and c appears twice. Nice, let's call this 1. Okay, now our second group, let's take the second one and the third one. So we'll go c squared a squared plus a squared b squared bigger than or equal to, follow the same deal, 2 of the first thing that's not squared yet, ca, and the second thing, ab by Cauchy's. And so this is 2abc, except a appeared twice. Let's call this 2. And finally, we can consider the first one and the last one as a pair. Put them together. We have b squared c squared, a squared b squared, bigger than or equal to 2 for the same thing, bc, ab. And this time, if the pattern is correct, yep, b appeared twice. Let's call this 3. And remember what the trick was, right? Add them all together, divide by 2. But say you don't know why divide by 2. If I add all 3 together, I have b squared c squared c squared appear twice. So there's 2b squared c squareds. And have a look, I have c squared a squared appears twice. So 2c squared a squared. And finally, also we have a squared b squared appears twice. So add them together, 2a squared b squared bigger than or equal to, add them all, it's 2abc squared, 2a squared bc, 2ab squared c. Okay, firstly, we should divide 2 to everything, so 2's are all gone. And notice this actually is our answer, right? Because therefore we can conclude b squared c squared, this is c squared a squared, this is a squared b squared, bigger than again. All of them have a, b, and c, except one of them has a twice, one of them has b twice, one of them has c twice, and there's our answer. Done. Very neat. C. Okay. What is this? Okay, same idea. I'm going to try to get squares going on because another thing about this, if you don't have squares, say, so our theorem look like this, x squared plus y squared bigger than 2xy. If you don't have squares, it actually is fine. You can just have x and y bigger than or equal to 2, except it's going to be, as you can imagine, square root x times square root y, yeah? And that doesn't look very nice because none of our right-hand side have square roots. Perhaps square root and square root cancel out to give us just a normal looking number, but I wouldn't count on it, so I want to make it look as nice as possible. So again, we're just going to, for the same deal, I'm going to try to aim for as this grouping squares together. Expanding 3 of these is very annoying, but if you understand how binomial expansion works, hopefully you can very easily kind of inspection expand, right? What's the trick to inspection expand? It's just, you need to, when you expand it out and multiply them all together, it's very much like you pick one from here, multiply by one, just one from here, multiply by one from here, yeah? And you do all possible combinations, and that's it, right? So what's one possibility? It could be I pick the B, pick the C, pick the A, and times them together, it's A, B, C. What's another possibility? I could have picked the... I could have picked the... Say what? I could have picked the B, I could have picked the A, I could have picked the A, I could have gotten A squared B. And if you just imagine all of them, just all of them is just going to be one from B or C, one from C or A, one from A or B. And if you write them all out, I hope you can see it's going to follow a nice pattern. And A squared B, AB squared, A squared B, AB squared. And if I choose another two, it should look like AC squared. Maybe I should do B and C first. BC squared, B squared C, and AC squared, A squared C. And now, do I have all of them? Actually, it looks like I have all of them, except I'm missing one. Notice that all of these, with one squaring and the other one has a single one, like A happened twice, B happened once. Notice this can only happen one way, right? It can only happen with A's appearing twice and B appearing once. There's no other way that A can appear twice and B appear once here. But also notice I have now 1, 2, 3, 4, 5, 6, 7 terms. And notice if I expand it all out, this is 2 to the 3, should be 8 terms. What's the one that's missing? Notice I can get A times B times... A times B times C. That's one way to get the term ABC here, this term, right? But I can also get it A times B times C this way. So there's two ways I could have gotten ABC, and therefore I actually would have another ABC term. If you don't like this type of expansion, well, feel free to just FOIL expand this and then expand the whole thing out at the end. But this is a nice way to inspect and span, right? Left-hand side is therefore this whole thing. Once you get good, it's pretty fast. And now the game appears again, and it looks like we have something really similar to this above. Yeah, our first one looks almost exactly the same. There's two ABCs, we group them, and now we already know the trick. We want to group the single B and single B. We get A squared plus C squared. We want to group the single A and the single A. We get B squared plus C squared. We want to group the single C and single C. We get B squared and A squared. And once again, just follow Cauchy's inequality, second case. A squared plus B squared bigger than 2AC. B squared C squared bigger than 2BC. You'll write it out properly, of course. I'm just cheating. 2AB. And therefore, this is larger equal to 2ABC. There's another 2ABC. There's another 2ABC. There's another 2ABC. There's 4 of these. It's 8ABC, which is my right-hand side. Nice. Left-hand side bigger than equal to right-hand side. Cool. Now, D. Whew. Okay. Well, I mean, we learned our lesson already, right? Expand, try to group squares so that we have square plus another square, and hopefully we can use our AMGM inequality second case. So expand it out. This one's just a multiply. So left-hand side, expand out. A times it together. A squared bx plus AB squared y plus A x squared y plus bx, y appears twice, y squared. Okay, how do I get my squares together? Oh, there it is. Look at these two terms. They both have a y in it, so I can take out a y, and I'll have in b squared plus x squared. And hopefully these two terms, look at them, they both contain 1x and 1b. I can take that out. 1x, and 1b. And what's left is a squared, y squared. And apply exactly the same deal. This is larger than or equal to 2bx. This is larger than or equal to 2ay. So in total, this whole thing must be bigger than or equal to 2. This is a, b, x, y. This is also a, b, x, y. 4a, b, x, y. Right hand side. Nice. Okay, last one. This one looks the easiest, but it looks the most different from everything we've seen so far, and that is not very hopeful, but hopefully it's not that hard. Okay, see, what's different, but also what's neat about this, it's different to the previous, but it's actually the same. Why? Because all the others is we can hopefully gather x squared, say one thing squared plus another thing squared bigger than or equal to. So left hand side should have a bunch of squares and should be bigger than to some right hand side, which looks kind of nice here. But instead, look what we have this time. We have, back in our formula, x squared plus y squared bigger than 2xy. Instead of having our squares on the left hand side, we now have our nice looking things on the left hand side. So essentially, and it's smaller or equal to, if you can see it, hopefully you can see it, it's essentially this thing flipped around here. So we are going to use the theorem 2xy smaller or equal to x squared plus y squared instead. Or in this case, there's no 2, so let's make it look easy. By x squared is smaller than x squared plus y squared on 2. So I'm going to use this, and hopefully it's going to come up with the answer really quickly, especially given these square things cancel out very nicely. Let's try. So we have left hand side is ax plus by. Now let's have a look at them individually. First up, ax is smaller than or equal to two things multiplied, smaller or equal to each individual squared, divide by 2. Same with this, each individual squared, divide by 2. And I think you'll see it works amazingly. So therefore this expression is smaller than a squared plus x squared, they're all on 2, plus b squared plus x squared on 2. And this thing is, look, a squared plus b squared, I should group together. And, whoa, mistake, whoops, it's a y. So this is meant to be a y, this is meant to be a y, this is meant to be a y. And so I have a squared, b squared, group x squared, y squared together, and a squared, b squared is 1, so that's half. X squared, y squared is half, 1, so it's half, it's 1. Left hand side smaller equal to 1, which is right hand side. I'm also done. So, pretty neat. And I guess it's a nice testimony to good old maths working, and also how powerful the Cauchy's inequality second case can be. This is indeed a very powerful theorem. And also, don't forget our neat tricks. Expand. If you're still not sure, maybe backwards reasoning, but we didn't have to for any of these cases. But don't forget it's always there. And also don't forget this neat trick. When you have 3 things squaring, bigger than or equal to something, typically it's a nice idea to take 2 at a time and apply Cauchy's second. Okay, that's it from me. Do out.